Now let's work with some algebra of functions. F plus g of 1 is the same as f of 1 plus g of 1. However, notice we are not distributing the of 1. That is not a multiplication of 1. It just happens that the notation looks this way. When I substitute 1 into f, I get the square root of 1 plus 3. When I substitute 1 into g, I get 1 squared minus 1. I get the square root of 4, which is 2, plus 0, and this expression is going to equal 2. If I want to find f composite g of x, I can take the g of x and substitute it into f of x. F of x is the square root of input plus 3. So here's my input plus 3, and it's going to be x squared minus 1 that's being substituted in. This will now simplify, and we can rewrite this as the square root of x squared plus 2. When we have a composite function with a number as the argument, we want to take the 4 and substitute it into f, and then take the output of that and substitute it into g. So let's begin with f of 4. That becomes the square root of 4 plus 3, which is equal to the square root of 7. That then becomes the input into g. G of root 7 is equal to root 7 quantity squared minus 1. That's 7 minus 1, which is equal to 6. Now, let's find the domain of the sum, difference, and product of these functions. Let's look at f of x and g of x separately. F of x is equal to the square root of x plus 3, and therefore we know that x plus 3 must be greater than or equal to 0, and therefore the x must be greater than or equal to negative 3. G of x is x squared minus 1, and the domain is all real numbers. There are no fractions, there's no square roots, and there's no logarithms, so there's no restrictions here. To find the domain of the sum, difference, or product, we're taking the intersection of these two conditions here. And basically, when you overlap these two, it turns out that our domain is going to be x greater than or equal to negative 3, as written here in interval notation. However, when I take and look at the domain of f divided by g, I begin with our domain that we found up above in part D, and then we have to also make sure that we're not dividing by 0. So I've got to take a look at that g of x, and that's x squared minus 1, and we need to make sure that that's not equal to 0. And that means if we factor the left, that cannot equal 0, and therefore x cannot equal plus or minus 1. Now technically I just solved a non-equation using properties of equations, and that's kind of bad news there, but I think you understood what I did. Now initially we said the domain, let's take a look at our number line, negative 3, negative 1, and 1. Initially we said the domain was going to be all these values from negative 3 and above. But now we're saying, uh-oh, we got a problem at negative 1, and we've got a problem at positive 1. So I have to skip over those values and write the domain of this quotient as negative 3 up to negative 1, which we don't include, united with the numbers between negative 1 and 1, united again with the numbers to the right of, but not including 1 itself. Okay, let's find the inverse. This is kind of a messy problem here. I'm going to rewrite this as y equals 2x plus 3 over 7x minus 8. And the first step of finding the inverse is to do the switch of x and y. That means we're going to have instead x is equal to 2y plus 3 over 7y minus 8. Now we've got to solve for this value of y. To do so, I'm going to put the x over 1, and I'm going to cross multiply. One diagonal becomes x times 7y minus 8, so I will write that as 7xy minus 8x, and the other diagonal will be 2y plus 3. Now, since I'm solving for y, I want to get all the y's on one side, which means bring that 2x to the other side, and we want all the constants, or the rest of the problems, to the right, so I'll subtract off or add 8x to each side. This gives me 7xy minus 2y is equal to 8x plus 3. I can then factor a y out on the left, leaving me with 7x minus 2, and the right side is 8x plus 3. We'll then have y equals 8x plus 3 over 7x minus 2. Now let's find the domain of what we just found up above. Basically, we need to look at this 7x minus 2 and make sure that 7x minus 2 is not equal to 0. Therefore, 7x cannot equal 2, and x cannot equal 2/7. Now you notice I cheated here. I solved a non-equation using properties of equations, but I think you know what I did. And so the domain of f inverse is going to end up being from negative infinity up to 2/7 united with 2/7 to positive infinity. Now, to find the range of f inverse of x, I don't think we're very good at finding the range of things we don't know how to graph yet. So basically I want to use an idea. The range of f inverse should match, matches the domain of the original function f of x. Just as x and y trade places, the domain and range trade place. So if we look at f of x, which was 2x plus 3 divided by 7x minus 8, we should now be able to look at the domain of this, saying 7x minus 8 is not allowed to equal 0, and that should match the range of f inverse. 7x is not allowed to equal 8, and x is not allowed to equal 8 over 7. So more specifically, written in interval notation, we will have negative infinity to 8/7, which we do not include, united with the numbers to the right of 8/7.